Dear participants, in this session, we will go forward with some basics of temperature measurement. As we have already studied in our theory coursework, there are several different temperature sensors. We have studied about resistance temperature detector or RTDs. We have studied about thermistors, thermocouples, and there are other semiconductor sensors like AD590, LM35, etc. In this session, we will be just going through the behavior of RTD and thermocouple. Here, for this experimentation purpose, PT100 is the representative of RTD and K-type thermocouple has been used. This very simple experimental setup has been used here. This is made by Scientech, Indore. It is actually an extension part of the Scientech Composite Experimentation Kit 2311 that we have seen in our LVDT experimentation. So here you can find, let us now first understand this experimental setup. You can see here there are 4 different temperature sensors. Here you can see there is RTD, it's like this. This is actually PT100 RTD. Since this is just for demonstration and we do not need very precision, 2-wire RTD has been used here. This you can see is a K-type thermocouple. This is an thermistor NTC type and this is LM35. Now you see here why they have all been embedded into that metallic block. Basically, there is, you can find here, this is actually a high wattage reheater that is in physical contact with this metallic block. When we actually connect a 12-volt supply and ground, a current flows through this high wattage resistor. So this 12 volt is connected to one terminal of the resistance on this side, that is connected inside, okay, and on the other side ground is connected. So what happens, that current flows heavily through this resistance and definitely power is dissipated in the form of heat simply because of Joule's law, I square RT, and that heat is immediately communicated to this block. This is an aluminium block. Aluminium is a good conductor of heat. So immediately heat is passed to it and this block gets heated. Now these sensors, since they are embedded into the structure of this metallic block, they are in contact of that heat. So accordingly their behavior changes and we are able to see that how these sensors behave under temperature. Now you see here we will be studying RTD and thermocouple. Remember that here this NTC, RTD, thermocouple, they are all having their contacts available for our experimentation purpose. You can see here, these are the two wires of the RTD. These are the terminals. Be very sure that they are not internally connected anywhere. This is the thermocouple. Again, you see here, these are the two terminals. However, remember that for thermocouple, we should be very clear of the polarity. That's why you can find this polarity symbol has been given, this plus and minus. You can find here. That we have to remember. Now there is also a fan. You can see this is a small fan. It is again operated on 12 volt DC. So if we take the connection of this 12 volt and ground to the fan and we operate this switch, the fan rotates. So when we want that the temperature of the metallic block should decrease, we disconnect the heater and we can put on the fan so that this metallic block can be easily cooled. Now you see here, the purpose of this LM35 is to show the temperature of this metallic block. Now why LM35 has been used? You see, this LM35 has got factory calibration in such a manner that for 1 degree change in centigrade, 1 degree centigrade change in temperature, there is a 10 millivolt change in the output terminal of LM35. Basically, LM35 is a 3-terminal device. One of the terminal is connected to supply, other to ground, and the third one is output. So when the temperature is raised or lowered, very precisely, there is 10 millivolt change for 1 degree change in temperature. So therefore, easily we can connect a multimeter, and when there is a change of certain millivolt at the output of the LM35, we can easily understand what is the temperature of this block. Therefore, this LM35 is connected here. It is situated here inside the block. However, we will not be using LM35. We will be using a direct temperature display for our purpose. Okay, so we will not use this. Now you can find there is an amplifier. This is an amplifier block. A simple 741 amplifier has been used here. That's an op-amp. Here, the voltage that is developed across two terminals of the thermocouple is fed to the input of this amplifier, and we can have an amplified output. Again, we are not going to use this. We will directly read. Now, why this amplifier is given? You may see that this thermocouple, K-type thermocouple, the change in voltage is very small. They are in very small steps of millivolts or in tens of microvolts. Therefore, it is hard to be read. That's why this signal conditioning is required. Now you remember here, for our experimentation purpose, we will not go for any signal conditioning. That means whenever the temperature will change, you will find change of resistance across these two terminals. So that means when the temperature of this block will be raised, very simply, the temperature of temperature that is applied to the RTD will change, and definitely, since this is a resistance temperature detector, fundamentally the resistance will change. We will only look into this change of resistance. This is going to be a very simple phenomenon. All right. Now see here that the output of this RTD, if we want to see it directly, that is of no usefulness so far the reading is concerned. Definitely, the physical parameter that is changing is temperature. Accordingly or proportionally, the resistance is changing. That is all good for us. But unless we condition the signal to show us or to display us the temperature, we are unable to understand what is actually the temperature here. So again, there is the necessity of signal conditioning circuitry. Here we are not going for the same. Next comes the thermocouple. Now you see here, I must mention this PT100, the particular sensor that we are using here. It is having a very wide temperature measurement range. It can measure from minus 200 degrees centigrade to plus 850 degrees centigrade. And normally, I should say typically, per degree centigrade change will bring about 0.385 ohm change across this device. This is a typical value. Next comes this K-type thermocouple. As we know, the K-type thermocouple is having two different metals that are joined. Basically any thermocouple, you can see here, I am getting one thermocouple for example. I will show it closely. You can see here this is a thermocouple and you may find this is the junction. This is the junction of two different metals. I don't know whether it is properly visible, but you can see two different wires over here. These are the two different metals. Now, since these are the two different metals at a junction, and when two different materials are there, they are joined, and two junctions of these dissimilar metals, they are kept at different temperature, and EMF is generated. Simply voltage is generated. So this is according to the Seebeck effect. So the thermocouples, they work on the principle of Seebeck effect, and the different metals that are used here, that is, this is the sheath actually. This is the sheath in both cases. This is the protective sheath. So this protective sheath is having a very close contact. Here in this case there is no protective sheath. Okay, so this you can think is the jacket, metal jacket, so that heat can be very easily transmitted. Whenever you are going for industrial measurements, so you can find a complete structure, I would like to show you. Here you can see this is the protective head and sheath. This is the Rtd structure, and it is something like this, okay. It looks like this. Now you see again the output of the Rtd directly is of no good. Therefore you need a transmitter. So such type of transmitter changes the change in resistance of the Rtd in terms of current. So such type of temperature transmitter normally outputs a signal of 4 milliampere and 20 milliampere. So minimum 4 milliampere and maximum 20 milliampere through the range of this Rtd. Now you see here such type of transmitters are also used that can be directly networked, and nowadays IoT based transmitters are also coming. These are the different temperature transmitters. You can see such type of temperature transmitter. It is I should say heart protocol ready sensor, okay, transmitter. So such type of advancements are there, but here we are talking about very basic principles, okay. So the dissimilar metals, the two different metals that are used here for this K-type thermocouple is chromel and alumel. Chromel is a composite of this nickel and chromium, it's an alloy, and this alumel is nickel, aluminium, and a very certain percentage of silicon is also there. So this is a composite material, And you see this, in case of this chromel, nickel and alumel is used actually. Nickel and chromium, that's why the name chromel, nickel and chromium. And alumel means nickel and aluminium, that's why alumel. All right, so this chromel, that constitutes the positive terminal, and this alumel, that constitutes the negative terminal. So now I will be putting this here. So I hope we are now comfortable with the basic experimental setup. What we will do, we will be applying a 12 volt here, a ground here. For that I will be using an external power supply. You can find here, this is the output from the power supply, 12 volt supply I am using. I am simply using an adapter for that, so that I will be connecting here. So when I give the supply, current will flow through the resistance and simply the temperature will increase. Now in order to see that temperature, I'll be using this device. You can see here again, this is a temperature controller, very low cost temperature controller, but you can again achieve a high accuracy with that. There is a relay, so that you can program this controller to connect or disconnect the heating supply through this relay. There are 4 terminals. 2 of the terminals are used for supplying 12 volt and ground, and the other 2 terminals are connected to the common and NO terminals of this relay. Here you can see through this relematic connector, this is the sensor. Again you can find this is a PT100 only. So I will somehow this plus 5 volt and minus 5 volt is not required for our purpose, because this plus 5 and minus 5 volt are required for this amplifier unit. So we will not be using that. What I will do, simply I will stick it here so that we can have the reading stably. And where actually the LM35 was supposed to be there, I will be putting this sensor. All right, so it is here right now. So we will be able to get the temperature here. So I will be putting up the fan that is there, so that we can have an undisturbed reading. So now our experimental setup is completely ready. I will put on. So you can see here the temperature that you can find here of the metallic block is 30.1 degrees centigrade. Okay. So next what I will do, now the heating has started. All right. So we will be connecting the 2 meters. I'll be taking here 2 meters. Okay. Fine. It will take some time for the temperature to rise in this metallic block. Now you can see the rise of temperature has started. So we are going from 30 to 30.1 like that. So here you can see for the RTD, we will be keeping our meter in for the measurement of ohm, and we are in the range of 200 ohm. Okay. So let us go for that. Since we are measuring resistance, this polarity is not a factor. So definitely if you want that resistance to be converted to voltage, then you can simply use a voltage divider network, where you can use this RTD as one of the resistance component, and you can measure the voltage across it. So you can do signal conditioning like that. So I will be measuring the resistance here. Okay. So you can see here, you have to check this temperature, and you can see that very precisely there is an increase in resistance. The funda is very simple, that whenever the temperature of any metal is raised, their resistance changes. So here the changes means the resistance increases definitely for a metal. So here you can see it is very precise. You can find, you can see here there is change of temperature in terms of zero point 0.1 degree centigrade. Gradually it is increasing, and you can find this is also increasing very gradually. All right, now let us concentrate on this thermocouple. Now for thermocouple, let me tell you one thing, that the changes are very slow. You see that K-type thermocouple is able to measure a temperature in a very wide range, and that's why it is very extensively used. It is not costly, accurate, precise, but definitely they need both of them. They need complex electronic circuitry for signal conditioning. So normally this thermocouple is connected across PID controllers or transmitters, where the ready-made signal conditioning circuitry you can avail. So here you can see that it is very hard to find the output, so the change is so small. You can see I am in now 200 millivolt range, so we have to be patient here. So the output is now you can see the output is trying to change across it. Now this meter, here you can see the reading in millivolt. In this meter, here you can see the reading in millivolt, and here you can see the reading in ohms. So here you can see as the temperature is changing, the change is very gradual, you can easily note it. But here the changes are very slow, because actually you are uh, using a particular sensor which is made for a wide temperature measurement. Okay, so they are, and the output of this is always very low, so we have to be very patient to see a change in output. Now you can see here the temperature change is fast, and it is also gradual. You can see a linear behavior. Now you can see that there is an effort to change, and now it will change after a while. Now you can see the voltage across, the voltage that is developed across this thermocouple, it has changed. Now see here, you have to remember one thing again, that this RTD, it is actually giving out the change in resistance. So in order to read proper signal from this RTD, you have to apply external signal, and the voltage biasing is required. But you see this thermocouple, it is an active device actually. It can generate a voltage at the output. So now what I will do, I will just you can see there is change. I will just go for certain which is not actually not expected, but I will do that to show you that yes, the temperature changes. You can see here the temperature is increased up to 44.3. I can also feel that yes, it is getting warmer. Now you can find that it is 0.3 millivolt. So what I will do, in order to go for a fast change, to see just whether it really changes or there is some fluctuation, that we have to be sure, isn't it? You might not believe what I say. So I will do some shortcut. I will use my soldering gun. You see here, this is my soldering gun. It's quite hot. All right. So what I will do, I will get in contact of that. Now you kindly read the output of this thermocouple. You can find very easily that I am giving physical contact of the soldering gun. You can see how fast it is changing. Can you see that? It's just jumping. So that means it is very fast also. Don't think. But the temperature rise has to be that much fast because it is working on a very wide temperature of. Now you can see I have removed this and how fast it is coming down. So don't think that it is slow, but for how much change in temperature? The temperature change also we have to be very honest, you know. If it is very slow temperature change, it will also respond slowly. But now you can see because of this temp reading change is so fast. I have removed the gun. Now you can find that it is coming down very fast also. So I hope that you have understood the operation, this thermocouple. Now I will put on the fan. I will put it here inside. There will be nothing, no reading here. Now let us concentrate on this. The resistance has increased like anything. So now I will be removing this 12-volt supply and I will be connecting it to the fan. I will operate this switch. So now the fan has started operating. Okay. Now you can see the temperature is coming down gradually because of the working of this fan. And while the temperature is coming down, you kindly note here. As the temperature was increased, the resistance was also increased for this RTD. Now as the temperature is coming down, the resistance is also getting lowered. We will wait for a while to see the trend. So now you can see the fan is rotating. Okay, you can see the fan is rotating, this fan. Therefore you can find that this is also coming down. The resistance is also getting decreased. So we can definitely note down the temperature in x-axis and note down the resistance value in y-axis and plot the characteristics of these sensors. So definitely those things will take time. I thought that I should just show you the phenomena. Whenever you are starting some measurement, suppose you are measuring a temperature, your start temperature, your measurement starts at say 31 degrees centigrade. Okay, at that time this reading is 110. I am just saying for example 110 ohm. So when you are coming back and this temperature decreases till that 30 degrees centigrade, it should be 110 ohm. If there is any deviation, that is known as hysteresis of the sensor. So such type of hysteresis is never expected. So that is one error. So you definitely through your coursework you have come across the terms accuracy of the sensor, resolution of the sensor, working range of the sensor, sensitivity of the sensor. So all these definitions you should know very clearly, because when you are going for certain application, all these things will be required at a time. So that's all with this demonstration. I hope that you are very thorough with this idea. And for any of your confusion, kindly comment in the comment box so that we can come with answers for your questions. Thank you.